It seems to be buffering the place for doing the wrong work. Is the mouse actually? No, the mouse disappears. I used the wheel on the mouse. That's it. What do we need to get to human level AGI? We talk about what's missing. When I think you do need the ability to recognize and generate patterns, which is what current neural nets are doing well. I mean, obviously we do that. We recognize and generate patterns. And actually, we often do it without knowing what we're talking about, just like a neural net does today. Like my 1-year-old daughter last night I was home before coming here, tried to get her to go to sleep. She's like, I don't want to go to sleep. Sleep is boring. And I know she doesn't know what boring means, right? She heard someone say sleep is boring. She figured that was an appropriate thing to say, and that's it. I mean, that's sort of like ChatGPT does. It's synthesizing something that sounds plausible given the context. And that, she says that, she sees how we respond, and then she learns something. So we do need to do pattern recognition and generation, but we also abstract in a way that current neural nets seem not to. And this relates to the huge number of parameters in current neural nets, right? Because I mean, you have many billions, tens, hundreds of billions of parameters. And I think being that big is not necessarily good. I mean, I think the more you've abstracted, the more compact your knowledge base can be actually. If you need to have a really, really huge collection of data, that means you're probably not doing that much abstraction. And I mean, if you look in statistical learning theory, there's something called minimum description length principle, right? Like compacting something smaller, a more compact description generalizes better beyond its training data. Now of course, there's more subtlety than that. You could have a very large model that generalizes well under some circumstances. But I think one way or another, you need to come up with concise, abstract, approximate summaries of your experience, rather than just having a huge list of special cases in your mind. And we ground patterns, abstractions, we ground linguistic patterns in observations, right? So like when my 1-year-old says sleep is boring, she knows what sleep is because she knows she sleeps. And eventually she'll learn what boring is because she'll hear us say like, waiting in line in the airport is boring or something. And then the grounding of the words in non-linguistic experience certainly gives nuance that you don't get just by connecting words to each other, which ties in with the ability to distinguish truth from nonsense, right? Because if you're not grounding anything in non-linguistic experience, it's very hard to distinguish truth from nonsense. Creating fundamentally new things, we know how to do that in a way because evolution does that. We have evolution of species. We have the evolution of life from bubbling clay pools on the early Earth, right? So it's clear that evolution, which combines pieces of one thing with pieces of another thing and mutates it, it's clear that this is an engine of creativity. And there's a theory called neural Darwinism from decades ago that explains how the brain can do evolutionary creativity by a sort of natural selection among neural assemblies, right? So I mean, we know how creativity can work, and there's been neural nets that do evolutionary learning. It's not how current deep neural nets are operating. It's a different sort of way of organizing neural net, and I think you do need something more evolution-like inside your AI mind to get creative improvisation. And reasoning also plays a role. I mean, most people don't reason that elaborately in everyday lives. On the other hand, if you're going to prove a math theorem or create a new biological hypothesis or build a machine, you're carrying out long series of reasoning steps. And this also comes up in other contexts. Certainly, it comes up in military strategy. Even if you're fencing, if you're sword fighting, you're planning 5-10 steps ahead, and you're carrying out a lengthy reasoning chain. And this is something current neural nets don't do. It's quite important. And understanding yourself and the other person you're interacting with, the other mind you're interacting with. Clearly, this is what psychologists call theory of mind modeling, right? We model what's in the other person's mind, and then we learn something about their reactions from that. And finally, there's the capability to develop, to fundamentally change yourself. In psychology, we distinguish learning from development. Learning, you're basically keeping yourself the same, but you're gaining new skills and abilities. But between age 2 and age 56, which I am now, I haven't just learned new skills. Like my whole way of thinking and being has changed a few times in that interval, right? So we're developing, we're continuously morphing ourselves into fundamentally new systems that have some resemblance to our previous version. And this requires an ability to modify and improve ourselves. Now, again, humans are limited in that. Like, I don't know how to refactor my dopamine receptors or something, right? So I don't know how to change the way my glial cells work. So we have some things we don't modify, but there's a lot of developmental plasticity over the human lifespan compared to current AI systems, which each system has its fixed architecture. And then you do an upgrade, like you throw out GPT-3 and get GPT-4, but GPT-3 didn't progressively morph itself into GPT-4 or something, whereas humans do develop in that way. So these things are all needed, and we have some understanding in the AI field how to do each of these, and there are prototype systems and loads of research papers on each one of these things. But none of them has been put all together into one practical AI system actually doing stuff, right? And there's a lot of possible approaches to breaking through this barrier and getting general intelligence to really work. My own approach is now centered on a software system called Hyperon, which is a new version of a system called OpenCog. So OpenCog, my colleagues and I started building in 2008 based on some code that went back to 2001 or something. We decided 2 years ago to refactor the OpenCog code base into a new system, which we're working on now. The theory underlying this is fairly deep, and I won't go into it in too much detail, but there's a paper on archive.org that I wrote called The General Theory of General Intelligence. If you look at that paper, you can see the cognitive and math and computer science theory behind this. And there's a series of, 10 videos on YouTube I recorded stepping through that paper almost line by line. So the core conceptual notion, you're viewing a mind as a system that recognizes patterns in itself and the world, including introspectively recognizing patterns in what it has done or should do to achieve certain goals in the world. And the core data structure there is a big knowledge metagraph, which is it's sort of like a graph in the computer science sense. You can have links pointing to links. You can have links going between 3 or 4 nodes instead of 2 nodes. You can have links pointing to whole subgraphs. So it's a slightly generalized graph. So we have this knowledge metagraph. It lives in RAM on multiple network machines. It also lives in a backing database on disk. And we represent both knowledge and learning and reasoning algorithms. They're all represented in this knowledge graph. So both the algorithms and the data, the programming data, are all the same. They're in the knowledge graph. And then parts of the knowledge graph are active, and they act by transforming the knowledge graph. And then you have neural net algorithms in this vast self-organizing graph. You also have probabilistic logical reasoning algorithms. You have evolutionary algorithms. But all of the algorithms are parts of the graph that are engaged with rewriting parts of the knowledge graph. And so this is OpenCog system, and there's two key technical components. One is the knowledge graph is called the atom space, and the nodes and links are called logical atoms. There's a distributed knowledge graph component. Then we developed a new programming language called Meta, which is stands for Meta Type Talk, which is basically a programming language designed to compile into a graph to make parts of the graph rewrite other parts of it. So for computer science programming language geeks, it's a fairly abstract language, which is, I guess, a probabilistically, gradually, dependently typed language. So if anyone ever played with weird languages like Idris or Agda, it's sort of the next step beyond that in use of dependent typing. Which is a sort of language that not many humans are going to want to program in. But it's mostly, we're programming it, but it's mostly intended for the AGI to be reprogramming itself, right? So it doesn't need to be that human friendly. So yeah, this is a rough diagram of this particular AI system. I mean, the SingularityNet platform is a blockchain-based sort of deployment layer that lets you run all this stuff distributed across many different machines with no central control. So the blockchain is used to allow decentralized coordination of many machines in the infrastructure. Then you have the atom space, which is shown to the right. You have the language interpreter for the meta language, which is called Adamese there. And then various AI algorithms shown on the left. Neural net libraries, probabilistic reasoning, evolutionary program learning. And for neural networks, we're not running every neural network inside this knowledge graph. So we can run a neural network in PyTorch or whatever toolkit you prefer, and then we can interface that with the Hyperon system. And if you have worked with PyTorch or things like that, in PyTorch you have explicit access to the computation graph. So you can take the compute graph of PyTorch and you can pull it into the knowledge graph in OpenCog and manipulate and reason and then modify the compute graph and export it. So we're taking this knowledge graph manipulation and reasoning system, and we're like hybridizing it and connecting it with neural models written in modern neural net toolkits. So one example, which I don't have a slide on, but I'll just mention it. One example we're working with, you can take a large language model. Could be ChatGPT. We're not using that. We're using our own large language model because we wanted free API access that unlimited amount. So you take a large language model of that nature. You can then use certain methods to extract logical knowledge from it. So you basically use few-shot learning to train the large language model to output predicate logic formalizations of what it knows. So then when you've gotten the language model to export logical versions of what it knows, then you have a large logic knowledge base representing what the language model learned. You feed that into your reasoning system. Then you can do generalization. You can do inductive, abductive, deductive reasoning. You can spot inconsistencies. You can then take that logical knowledge and you can use that logical knowledge to fine-tune the language model based on what the inference engine concluded, right? So you're interfacing the symbolic model for reasoning with the language model for pattern recognition. And there's a lot of different things you can do along these lines. this computer is running Windows 3.1. It's very slow. Okay, so there's a lot of depth in that previous slide, and if folks have a AI or computer science background, maybe you ask questions after the talk, and we can go into that more. But I mean, there's a fair bit of math and engineering there, which is hard to go through rapidly. I want to talk a little bit about scaling up now. So, neural nets were invented in the 1940s as a math and computer model of what happens in the brain. I remember teaching neural nets in University of Western Australia when I was an academic in the computer science and cognitive science departments. It was in 95, 96. We were doing recurrent back propagation. You had a neural net with maybe 30 or 40 nodes, and training it would take literally all day on the machines at the university, right? So, and you could do some interesting things. We had, conjugating verbs and so forth, and it could do a little bit of automatic handwriting recognition. It was doing something. The deep neural nets we have now they're a bit different, but they're not fundamentally different from the deep neural nets we were training them with recurrent back propagation, right? I mean, the biggest difference is we can just do, like instead of 30 neurons with a few hundred parameters, you have a few 100 billion parameters now, right? So, like, where's this come from? Well, it came from the internet, and it came from GPUs and massive multi-GPU server farms and so forth. So that having the right infrastructure helped tremendously in making these sort of same old algorithms do really cool things. And in a way that was luck, because GPUs were really invented for rendering computer graphics and video games, right? And then people found, well, wait, they also work for scientific computing. So it's partly that's the story of the power of mathematical abstraction, right? Because computer graphics and neural nets, it's all matrix multiplication. So as long as you can use your matrix multiplication libraries, it'll be fast. Now, symbolic AI, graph-based AI, evolutionary AI, doesn't necessarily boil down to matrix multiplication. And so the hardware infrastructure that has allowed neural nets to accelerate so tremendously doesn't so directly apply. You can certainly do it. You can use GPUs to accelerate graph-based and symbolic evolutionary AI methods, but it doesn't provide the same payoff it does applied to neural nets or rendering of graphics. And if you get into parallel architectures, at the base level, there's something called SIMD architectures, which is single instruction, multiple data stream. Then there's something called MIMD data structures, which is multiple instruction, multiple data stream. And roughly in SIMD parallelism, you have a bunch of processors, but they're all doing the same operation at the same time. In MIMD parallelism, you have a bunch of processors which may each be doing a different thing at the same point in time. And of course, the brain is not synchronous. The brain is MIMD parallel. Different parts of the brain are operating at different speeds and sending different neurotransmitters around and so forth. I mean, biological systems are kind of a mess, right? But an artificial neural net, you can boil down to matrix multiplication, which can then be done on the SIMD parallel hardware, like GPUs. Now, the need for MIMD parallel hardware for AI is not new. I mean, my friends Danny Hillis had a company in the 1980s called Connection Machines. Actually, it was called Thinking Machines Incorporated. Their supercomputer was the Connection Machine. It had 128,000 MIMD parallel processors, each doing separate things, programmed in CM Lisp. Right, so the need for this sort of hardware has been clear. While that company was ahead of its time and isn't around anymore. So now there's a couple initiatives I'm involved in aimed at sort of making scaled up infrastructure for these other kinds of AI, like symbolic and evolutionary AI. So one is a company called Simuli, based in Florida, actually making a bunch of novel chips. And the Simuli's AGI board will have a deep neural net chip, a CPU. It will have a chip for hypervector math, which is manipulation of very long bit vectors. And it will have a chip just for graph pattern matching. So that's a metagraph pattern matching chip. Then SingularityNet, which is a blockchain platform I run, lets you do distributed processing and distribute your compute across a wide network of machines, which may be owned by different people running on many different operating systems and doesn't need any central controller. So through tools like this, you can scale up infrastructure for a wider variety of AI tools. And now I'm running out of time, so I'm just going to zip through these last few slides, but this is fine. So what these last few slides just mentioned a few of the application projects that my team within the SingularityNet ecosystem is working on. And each of these projects has the property that you can do something valuable with today's technology, which is not yet general intelligence, but also these seem to be very fertile areas for general intelligence R&D, in that the more you advance toward general intelligence, the better you'll perform in these domains. And some domains don't need much general intelligence, like face recognition doesn't need much. You've just got such a big database of faces. There's not that much variety in human faces, and we managed to train really good models of face recognition, and without that much general intelligence. And some things are like that. Not everything is like that, right? So we're trying to understand human longevity, how to make humans live hundreds of years, thousands of years of healthy life. And what we have now, we have fruit flies that live 5 times as long as normal fruit flies, created by experimental evolution, which is just what we need is flies that live a really long time. We'll work on mosquitoes next. But by looking at the DNA of these long-lived flies, we're trying to understand why they live so long, because they were created just by evolving for a long time. Then use AI transfer learning to port that knowledge over to people, right? And the reason this would benefit from AGI technology is biological systems are very, very complex, and you just don't have that much data relative to the complexity of the system. I'm using the wheel on the mouse. I'm spinning it up and down. There we go. Yeah. All right. So, finance is another area. I'm not going to go into this much, but as you know, as society evolves faster and faster, financial systems enter into a new regime every couple of years. The historical training data is less and less relevant. You need systems that can learn based on a smaller and smaller historical sample, because what happened 5 years ago is no longer statistically similar to what's happening now. And robotics is the final area I wanted to mention. We've been working mostly on humanoid robotics, and we have Sophia, the world's first robot citizen, who was actually made a citizen of Saudi Arabia in 2017. Congratulations to Saudi for having that vision. And we have a couple sisters of Sophia. We have Grace, who's an elder care robot, and then Desdemona, who sings in a rock band. And the Desdemona robot is connected with a company called the Mosaic, which is using AI to generate music and singing and lyrics and so forth. Grace is associated with a company called Awakening Health, which is run by my colleague David Lake, who you're going to see in a moment, I think, which is, we're aiming to roll that out as a nursing assistant in hospitals. And these are each applications you can do without a breakthrough to general intelligence, but obviously would be able to do more and more the further you progressed. And of course, rolling these robots out in the world, they'll be gaining more data and more experience, and that then helps you train systems toward general intelligence. So, yeah, how is our robot friend doing over there? She's ready to roll? All right. So I think now I'm going to be quiet for a few minutes, and we'll see what our robot friend has to say.
Thank you, Ben.
I'm really good to introduce my colleague and business partner, David Lake from Hong Kong. And David runs the company Awakening Health, making Windows robot nurses, and also helps out a bunch with Singularity Net in various regards.
Thank you, Ben. Hello, everybody. Today we will have a very special presentation of Grace, the robot, talking about healthcare. And, you know, we've had a little bit of interconnectivity problems. I mean, one of the things that you have to understand about robots is that they are a machine. They're a machine like your cell phone, like your car, like anything, and you have to treat them like that. This particular machine needs very good internet connection. So we don't have that in this case today. So I'm going to run a script that we had prepared for the Global Healthcare Summit in Saudi about a month or two ago. And we were invited to Saudi by the healthcare minister to discuss the digital healthcare that we're working on. So I think that I would like to run this 13-minute, 14-minute program that Sophia will explain to you what digital healthcare is, where the healthcare market is going, and what she does as a healthcare assistant. There are only 10 such robots in the world today, and this is one of the ones that we call Grace number 6. So Grace 6 will be able to tell you a lot more, and it will be a very interesting time for you to do this. Afterwards, if you like, you can come take a picture of her, with her, a selfie, and you know, I can tell you some more about the robot. But today we will not run the interactivity where she will treat you like a patient. We will just simply run the speech that she made for the healthcare minister and the royal family. Thank you very much. Sorry, 1 second. We are just recalibrating the microphone. How is the sound going, guys?